Hi everyone. Today we are going to look at how to determine the local truncation error for some numerical methods. Okay, local truncation error for some numerical method, such as numerical method that you use to solve ordinary differential equation, such as RK methods and linear multi-step method. Okay, so we just want to look at these two methods. First thing I want to show the implicit Euler. So the implicit Euler, the update is given by yn equals to yn minus 1 plus h f of x and yn. Okay, now this is implicit because of the yn term appear in both sides of the equation. Okay, so the implicit Euler method has a Boucher tableau in this form. Okay, so what can we say about the local truncation error? What does local truncation error tells us? So the local truncation error denoted by this little n. So for this one, we will write as y as xn minus 1 plus h f of xn y at xn minus yxn. Okay, so what I did here, this whole thing minus with this one. Okay, so this minus with this. So y at n I can write as the exact solution of y at this particular point xn. Okay, now y xn minus 1 is the initial. So if I have a line number here, I have this one as xn minus 1, yn minus 1, and I have xn, yn. So to get this, I can also write whatever value of xn here. We know this is the step h, so I can say this is also equals to xn minus h. Okay, so my y at here, my y hand here. Okay, so this is similar with y at xn minus 1. Okay, just gonna write it properly. So I'm talking about the notation to write it. Okay, so the notation for this one will be y at xn minus 1. So to find the value of y at xn minus 1 is simply y at xn minus h, because I'm going back. Okay, so you have a negative sign here. So let's write this y at xn minus h plus h, if I can write it as y prime. Okay, this whole thing y prime at xn minus y at xn. Okay, so why this has become y prime? Because we are looking at our initial value problem. Y prime equals to f of x, y. This is our ordinary, it is our differential equation for the initial condition given as like that. So this is the initial value problem that we want to look at for the differential equation given as y prime equals to f of x, y. So when you see f here, I can write as y prime. Okay, so now what we do here, we can extend. Okay, we want to extend this in terms of series, Taylor series. So we have y of xn minus h y prime xn plus h2 over 2 factorial y double prime. Okay, xn, okay, obviously this is xn, but instead of writing an xn, maybe I can explain that later on. So just focus on this. So just consider three terms of the Taylor series expression for y at xn minus h, and then we have plus hy prime xn minus. So I'm just gonna erase the rest. Okay, so we have minus y at xn. Okay, this term here is here, this term here is here, and the expansion of this is here. Now why this is negative? So that if you have a negative sign, your Taylor series expansion will be negative, positive. If you have a third degree, it will be negative, and so on. Okay, so now what we have here, I can simplify. This term and this term cancels out. This term and this term cancels out. That leaves me with h2 over 2 factorial y double prime xn. Okay, so what I can say here, so I can say that the local truncation error has obviously there are some higher term here. Okay, h to the power 3 that I didn't extend. Okay, so we can say that the order of the method is 1, because for local truncation error, if you have h squared, the order is h to the power of p minus 1. Okay, so the method can be order 1. Now to come more detail about this, such as we want to talk about convergent. So what we do here, if you look at this term here, so I can write this as h2 over 2 factorial y double prime xn minus 1 plus h, right? So I'm going to have theta h. What is theta h here? So I've already explained to you, this is my xn minus 1, this is my xn, this is my y at xn, and this is my y at xn minus 1. And this is the step size h. So if you want to look at this term, I can also write y at xn minus 1 plus h. I get this point here. Okay, now why am I writing theta h here? So to check the convergence, I'm talking about convergence now. To check about convergence, I can say that if this derivative, the second derivative of x here, less than equal than m, for all x in initial to the interval xn, then I can say that the local truncation error is also less than equal of h2 over, so h2 over 2, and what is this term here? This is my m. For all n. So the method will be convergent for Euler method as long as the local truncation is satisfied in this term. Okay, where you can say theta here from 0 to 1. Obviously for this case we are looking at 1, right? Okay, so this is how to check the if you want to explain more about the convergence. Okay, now let's look at another method. Okay, let's look at this method here. So what is this method? So we have the implicit trapezoidal rule. Okay, so given by yn equals to yn minus 1 plus h over 2 f of xn minus 1 yn minus 1 plus f of xn yn. Now this implicit trapezoidal rule, I am looking at the Butcher tableau in this form. 0, 0, 0, 1, half, 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 half. Okay. Okay, so what I have here, the local truncation error will be yn minus 1 minus h over 2 f of xn minus 1 yn minus 1 plus f of xn yn. Okay, so I can write this as y at xn minus y at xn minus 1 minus h over 2. Now f will be y prime xn minus 1 minus, okay, expand the bracket, h over 2 y prime xn. Okay, now the tricky part here, we want to expand some of these terms in terms of Taylor series. Now our student will always get confused on which term to expand. Okay, the trick here is we want to cancel out as many terms as possible and just leave with one term containing the power of h. Okay, so if you look at this term, if I am expanding this term here, so I need to write this as y at xn minus 1, okay, plus h. Okay, if I'm expanding this in terms of series, and then I don't have to expand this, okay, because I already have a y in this term here. Now I need to expand either one of these, okay, so if I want to expand this term in terms of series, I will write it as y at xn minus 1 plus h. Okay, or, okay, let me just clear with you. So there could be either way. So I like to sketch to recall what I'm doing. Okay, so I can have xn minus 1 plus h to represent my xn. Okay, or I can also have, this is a point at y at xn, right? So what do I do here? I can have xn, okay, xn minus h. Okay, so you gotta be careful on what terms that you wanna expand. Okay, so now let's look at this term here. So expanding this term will give me, I want to use purple. So y at xn minus 1 plus h y prime xn minus 1 plus h2 over 2 factorial y double prime xn minus 1 plus h3 over 3 factorial y triple prime xn minus 1. That's it. I will have to write the order 4 term. I don't have to expand anymore. So I'm going to expand everything in the power of h cubed. Okay, so and then I'm going to write it down here, minus this term here, y at xn minus 1, minus this term here, y prime xn minus 1, And then I'm going to expand this term, h over 2. Okay, y prime xn. Okay, can you see the problem here? What happened? So I have the term xn. So that's why you need to expand this term. Okay, not y prime xn, because this should be y prime. Just write it properly. This should be y prime xn minus h. Okay, so expanding this will give you y prime xn minus 1, okay, the first term, and then plus h y double prime xn minus 1, and then the third term will be h2 over 2 factorial y triple prime xn minus 1. Okay, do I need to expand more? No, because I want to get h squared times h is h cubed. So I know the next term will be in the form of order 4. Okay, now you can see that how some of the terms cancels out. Like this term cancels out. Okay, and then look at y prime term. So negative will give you minus h y prime, positive h y prime. So all this term cancels out. And then you have term involving h. H times h is negative h2 over 2 factorial y double prime. So this term also cancels out. Now that's beautifully done. So I have the term h3 over 3 factorial y triple prime xn minus 1, the term here. Negative, bring it here, will be negative h3 over 4. Okay, 2 factorial times 2 is 4. Y triple prime xn minus 1, and you have h to the power 4 term. Okay, so this is good. So I hope you get the idea. You don't have to expand all this term. You choose the one you want to expand. If there's a 2 term involving y, okay, you expand either one. But obviously, if you want to expand this, it's also possible, but you have to expand this one next. Okay, so the idea is to cancel out the term. Okay, so what do I have here? h3 over 6. So I have 1 6 minus 1 4. h3 y triple prime xn minus 1 plus order 4. Okay, so what can I get here? So times 2, 2 minus 3, you have a negative h3 over 12 y triple prime xn minus 1 plus this order 4 term. Okay, don't worry about the negative sign here. But what we can say here, we can say that this, what we can say here, the conclusion here, the implicit trapezoidal rule is of order 2. Okay, why is it order 2? You can say that the h highest power is 3, so it will be 3 minus 1, which is order 2. Okay, this is how you expand the Taylor series expansion for RK method. And since I have time, I have some time now, I want to show you how the Taylor series expansion works for linear multistep method. Okay, let me just find the question regarding linear multistep method. So, okay, so we have this method. Okay, one more example on linear multistep method. Okay, so I'm just going to put it third order Adams Bashford method. Okay, so how can I show that this is a third order Adam-Bashford method? So I can okay, before that let me just write down how the Adam-Bashford method looks like. Yn minus 1 plus 23 over 12h f of yn minus 1 minus 4 over 3 h f of yn minus 2 plus 5 over 12 h f of yn minus 3. Okay, now student can get confused because obviously they haven't seen a function that have y, because all the while here we are looking at a function involving x, right? And now suddenly you have a function involving y. So it doesn't matter, it's just considering an autonomous form, okay, but they shouldn't be much different than how you expand earlier on. Okay, so the LTE, the local truncation error, can be written as yn minus this term or the whole term minus yn. So I want to do it slightly different. So yn minus 1 plus 23 over 12 hf of yn minus 1 minus 4 over 3 hf of yn minus 2 plus 5 over 12 hf of yn minus 3 minus with my yn. Okay, why I want to do that? You see the earlier problem that we solved here, you have a negative term. Okay, because what I did was I took this yn here, okay, so minus with this equation. So if you don't want to see the negative part, what you could do is this whole term minus with yn. Okay, but it doesn't matter because we know that local truncation error, it must be positive. So you have to take the absolute, but I'm not going to show that. Okay, now how to expand this? Okay, so this is not much different to change this in the form of x. So I can write this as y at xn minus 1 plus 23 over 12 hf of xn minus 1 minus 4 over 3 hf of xn minus 2 plus 5 over 12 hf of xn minus 3 minus y of xn. Okay, so I can still write it in the terms of xn. Now, we want to decide what term we want to expand, and this can be very tricky. Okay, so I can see y here and y here. So what I can do, I can either expand this in terms of xn, or expand this in the terms of xn minus 1. Okay, and then similarly for this term here, so there are so many y prime here. So let's write it first. So if I want to remain this, I can write this as y at xn minus 1 plus 23 over 12 hy prime xn minus 1 minus 4 over 3 hy prime xn minus 2 plus 5 over 12 h of f xn minus 3 minus. Okay, now I would like to expand this in terms of series, so I can write this xn minus 1 plus h. Okay, so why I want to do that? Because I know the first term in the Taylor series will be y of xn minus 1. Okay, which can cancel out this term. So that's the idea. Okay, now the rest here Okay, the rest here we want to show what term we want to expand. Okay, this can be very tricky because we want to cancel out as many terms as possible, and we know that the method is order 3. The hint is given order 3, so you must have a function in terms of h power 4. Okay, so writing this in terms of y of xn minus 1, so I'm not expanding this, but I'm expanding this instead, plus 23 over 12h y prime. Okay, xn minus 1, I can write it as xn minus h. Okay, I'm going to remain this as yxn minus 1 and then minus 4 over 3h y prime. Now this term here, I want to write it as xn minus 1 minus h. Okay, so the idea is I want to transform every of this bracket here in the form of xn minus 1. Then we can have some cancels out. So it will be 5 over 12h y prime xn minus 1 minus 2h. Okay, and then this term here as it is. So we have y of xn minus 1 plus h. Okay, so for those of you who are not sure why from here get to this term here, I can just do a quick sketch and explain to you all the points here. So we have here xn minus 1, we have here xn, we have xn minus 2, and xn minus 3. So for this term here, y prime xn minus 1 is here, so I'm not gonna expand this at all. But for this term here, xn minus 2 is this point, so I can choose xn minus 1 minus h to get to this point. And then to get to xn minus 3 here, I will start with xn minus 1 minus h minus h. So that's why I got negative 2h. Now I've explained to you for xn here. For xn here, y will become xn minus 1 plus h because I'm going forward. Xn minus 1 plus h gives me xn. Okay, if everything is clear now, what we do here, we just have to expand 3 terms. Okay, 3 terms for xn minus 1. Okay, so let's do that. So go back to my marker. So I don't have to expand this. Don't have to expand this. 23 over 12 h y prime xn minus 1. Now I do need to expand this, so take 4 over 3h. Expanding y prime xn minus 1 gives me y prime xn minus 1 because of negative term minus h y double prime xn minus 1. Negative will be positive, h2 over 2 factorial y triple prime xn minus 1. Okay, and then expand another term here. Positive will be negative, h3 over 3 factorial y to the 4th derivative. Okay, I hope you can see that. That's number 4 here. xn minus 1. Okay, close bracket. Continuing my next term here. Expanding the next term, 5 over 12. So I have plus 5 over 12 h. Now expanding y prime. So I have y prime xn minus 1 Now this is 2h, so minus 2hy double prime xn minus 1. Now negative will be positive h squared, so by 2h squared over 2 factorial y triple prime xn minus 1. Positive will be negative h cubed, right? So 2h cubed over 3 factorial y to the fourth derivative xn minus 1. Now close the bracket. Okay, and then now this term is already expand. This term already expand. All we have to do is this term here. So minus the whole bracket here. Y at xn minus 1. That's the first term. Now this is positive, so plus hy prime xn minus 1 plus h2 over 2 factorial y double prime xn minus 1 plus h3 over 3 factorial y triple prime xn minus 1 plus h4 over 4 factorial y to the fourth derivative xn minus 1. Okay, and then the rest is the term involving h to the power 5, which I don't wanna expand. So you write it like that. Okay, obviously this is a continuation. Okay, don't get me wrong. Okay, so now what we can do here, see, you should have equation that only involving xn minus 1. If you look at the inside term, that will make the cancellation more easier. Okay, so first term here, this term cancels out. Okay, you can collect all the term involving, so let's do that. Collect all the term involving hy prime xn minus 1, and then collect all the term involving h2y double prime xn minus 1, and then collect all the term involving h3y triple prime xn minus 1, and lastly all the term involving h4 to the fourth derivative xn minus 1. Okay, it's just too long. The equation is too long. Okay, and then order 5. Okay, so I can guarantee you, all this term involving y prime, y double prime, y triple prime will cancel out. Okay, let's check that. Okay, for hy prime, I have 23 over 12. Okay, and then I have negative 4 over 3. And then this one considered, and then I have 5 over 12. Okay, and then lastly, negative 1. Okay, negative 1. I'm going to write it as 12 over 12. 12 over 12 is 1. Negative 1. Okay, so that's hy prime term. And the second term involving h squared. H times h is h squared y double prime. So I have positive 4 over 3. Okay, this term cancels out. And then look at this term here, so already cancels out. Negative. Okay, write negative first. 5 times 2, 10 over 12. 10 over 12, h times h, h2 y double prime. This term cancels out. I mean, not cancels out, I've already considered this term. Now, inside here, I have minus 1 over 2. Okay, minus 1 over 2. Okay, that's the term involving h2 y double prime. Now, the term involving h cubed y third derivative. This is the third derivative, so I have negative h times h is h cubed y third derivative. So the constants are 4 over 3 multiply 1 over 2. So I have 4 over 6, negative 4 over 6. Okay, this term being considered. Now inside here, 4, h squared times h is h power 3. Okay, so 4 times 5, 20 over plus 20 over 12 times 2, 24. So you gotta be very careful when you are doing this, okay? And then this term already considered, this term involving h to the power 3 term and y the third derivative. I have 1 over 6. Okay, this term also considered. Now the remaining terms are involving h to the power 4, okay? H cubed times h is h to the power 4. Negative, negative, positive. 4 over 6 times 3, 18. Okay, good. Now this one here, let me see what's constant in the front. 5 over 12 times 8 over 6. Okay, 8 times 5 is 40, and make sure there's a negative. 40 over 6 times 12, 72. Okay, considered. And the last term will be minus negative 1 over 4 factorial is 24. Gosh, look at this. So complicated, but not that difficult, right? It's just picking up the constant. Okay, now what do you get here? 23 times by 4 times by 4. Okay, so we have 23 minus 16, which is 7 plus 5, 12. 12 over 12 minus this term 0. Now this term here, times by 4, times by 4, times by 6, times by 6. 16 minus 10 is 6 over 12. 6 over 12 minus 6 over 12, 0. Times by 4, times by 4, times by 4, times by 4. So we have negative 16 plus 20. 4 over 24. 4 over 24. Is it correct? Do I have a negative term somewhere? Yes, this should be negative, not positive. Okay, class, just check again. Okay, I'm pretty sure this must be negative, else this term won't cancel out. Let's look at my term here. H cube here, refer to this term here. Negative times 1 over 6. So it's 1 over, it should be negative. Then it cancels out. Okay, so always check, because we will know that Taylor series expansion will only remaining one term involving h power. Okay, so this term cancels out. Finally, leave you with term involving h power 4. So what I want to do here, multiply by 3, multiply by 3, multiply by 4. Multiply by 4, multiply by 3, multiply by 3. So what I have here, I have 16 over 72 minus 40 over 72 minus, okay, 3 over 72, h4 over 4th derivative, xn minus 1 plus order h to the power 5. Okay, so let's simplify this. What do you get? 16 minus 40 will give me with 24 negative. So I have negative 27 over 72 h4 y to the power 4 xn minus 1 plus order 5. So I can simplify this. with negative 3 over 8 divided by 9. Okay, so there you go. There you go. So my local truncation error is given by this. So I can say that this third order Adam Bashford is order 3. Okay, h to the power 4. So p minus 1 will be h to the power 3. So the method is of order 3. Okay, that's it. That's the end of derivation for local truncation order error for Runge-Kutta method and linear multi-step method. Okay, thank you for watching this video.